Hi, my name is Yannis Kazaridis and I will present you our work with the title eProfiler, a high-precision power monitoring system for IoT devices that feature extreme dynamic range of operation. This is a joint work with my colleagues Ioannis Zographopoulos, Nikos Sidiropoulos, Polychronis Simeonidis and our professor Thanasis Korakis. Modern Internet of Things devices and sensor systems exhibit extreme dynamic current consumption profile since latest microprocessors and electronics supports ultra-low currents in the sleep phase of only a few microamps or nanoamps while they expend several milliamps in the active state. This stems from the fact that they integrate state-of-the-art elements such as RF radios, power regulators, sensing modules, and microcontrollers that feature improved power characteristics as well as various operating and sleep modes. For example, the Waspmote device consumes several microamps in its sleep state while it draws several milliamps when active. In this video, we measure the power consumption of the Waspmote device using the Fluke 289 multimeter and the current ranger power meter that is able to accurately measure ultra-low currents even of a few nanoamps. Similarly, the EZ430 wireless mote expends roughly 10 milliamps when active, while it drains only a few hundred nanoamps in its sleep state. Other implementations, like the Icarus mode, also exhibit wide power consumption profile dissipating only 22 nanoamps in its quiescent state and again several milliamps in its active state. At the same page, energy harvesting circuits usually draw only a few nanoamp in their quiescent states, as for example the double dip system. Identical behavior is observed by energy harvesting power supply sub-circuits that exhibit wide dynamic currents that may vary from a few nanoamps to several milliamps. Consider, for example, this RF energy harvesting setup. In this experiment, we use a Waspmote device attached with a LoRa interface set to propagate frames every 1 second and an RF harvesting board manufactured by Powercast. We use the current ranger to measure the actual harvested current. In this small distance, only a few nanoamps are obtained. If moved closer the Waspmote device, we see that the harvester obtains a few hundred nanoamps. Only when moving the LoRa board very close to the RF harvesting device we obtain currents in the range of microamps. Existing power meters are incapable of measuring the expenditure of modern IoT devices in order to aid in the development of energy-efficient SIMs, since they usually support measurements from a few hundred microamps up to several milliamps. In order to effectively measure currents of a few nanoamps to several milliamps, a dynamic range of 1 million to 1 is required. The common principle to accurately measure the current draw of a device under test is to place a shunt-resistor of low impedance in series between the power supply and the device under test. The voltage developed across the shunt-resistor is proportional to the current draw of the device under test according to the Ohm's law. Thus, a fast acquisition device along with a proper amplification circuit can be used to sample the obtained voltage drop. The selected shunt plays a significant role in the accuracy of the entire system, thus it must be carefully chosen. It should not affect the operation of the device under test and also provide sufficient level of detail to the next stage. Consider that the device under test drains a few milliamps. In this scenario, a suitable shunt resistor should be of 1 ohm, since the voltage drop across this resistor will be 1 mV to 100 mV. This signal can be easily processed by an amplification circuit, as well as it does not interfere with the operation of the device under test. Assume now that the device under test drains a few nanoamps or a few microamps. It is impossible to measure these currents using the same setup, since the signal of the resistor will be of a few nanovolt or a few microvolt respectively, which is infeasible to prevail over the noise and parasitic thermovoltages. Thus, a resistor with a greater value must be chosen to provide the required level of detail. For instance, a resistor of 1 kΩ fits well with the microampere range, while an 1 megaohm resistor is required for the nanoamp range. Thus, when it comes to monitor the power profile of a sensor node, a resistor switch able to adapt among the different consumption ranges is required without interrupting the operation of the device under test. In this paper, we developed a dynamic shunt-resistor switch formed by 3 resistors that are enabled depending on the flowing current. Specifically, we bypass the 2 resistors when required using 2 load switches. For example, when monitoring milliamp currents, the 2 resistors are bypassed. When measuring microamp currents, the first switch is open, so the current flows also across the second resistor. Finally, when monitoring nanoamps, both switches are open. Notably, two ultra-fast comparators are used to drive the deployed load switches. Each resistor features its dedicated current sense amplifier, while the utilized ADC unit samples all the utilized channels continuously, since it is infeasible to adjust the ADC inputs in real time. Along with the signals being monitored, we also monitor the state of each switch in order to calculate the final power results in the end of the experiment. In this paper, we introduced the eProfiler. The overall architecture we followed is presented in this figure. A dynamic shunt-resistor switch that supports three different ranges is implemented, featuring a 1 ohm, a 100 ohm, and a 10k ohm resistors. The alternation of the resistors is realized through the high-speed comparators without the intervention of a logic unit that usually induces significant delays. The eProfiler also monitors the derived voltage rail that powers the device under test that can be used to infer accurate energy measurements, especially in scenarios when significant voltage rail fluctuations occur. The embedded PC we opted for is the Linux-based BeagleBone board, which is a low-cost embedded platform characterized by sufficient processing power capabilities, low power consumption, and several communication interfaces. The device features an external microSD used to locally cast the acquired measurements prior to the offloading process, so the only limitation in the measurement duration is the size of the card deployed. The other advantage of our meter is the programmable real-time unit integrated by BeagleBone PC, which is actually a fast microprocessor that has full access to the internal memory and peripherals of BeagleBone CPU. We utilized the PRUs in order to enable real-time communication with the deployed ADC, supporting fixed interval between its measurement cycles. Moreover, we use the PRUs to read the state of the comparators that drive the load switch at every measurement cycle. Lastly, PRU is also used to trace GPIO events of the device under test with ultra-low latency, in order to support the correlation of the obtained power measurements with specific activities of the device under test. The ADC we employ is the Texas Instruments ADS8332. The ADC features 16 bits of resolution, high SNR, high PSRR, and performs conversions at 500 kSamples per second. The selected ADC integrates a multiplexer circuit, thus supporting parallel sampling of up to 8 inputs, while the overall sampling rate is divided to the employed channels. So, for example, when monitoring 3 inputs, the maximum retained speed is 160 kSamples per second. The current amplifier we selected is the Meas 9923. The Meas presents excellent characteristics in all parameters, while its crucial benefit is its ultra-low input bias current, which is 1 picoampere. Most proposed power meters utilized current amplifiers with several microamps input bias current, which suggests that it is impossible to measure currents in the range of nanoamps and microamps using these amplifiers. To give a better understanding on how important this parameter is, please see this example. When using the INA 139 current monitor that features 10 microamps input bias current, the amplifier obtains and amplifies the voltage drop across the resistor, but at the same time drains extra 10 microamps itself in order to bias its internal circuits, which results in totally inaccurate readings. This finding suggests that only ultra-low input bias current amplifiers in the range of picoamps can be used to monitor currents in the range of nanoamps and microamps. Moreover, we utilized two ultra-fast comparators featuring 4 nanoseconds propagation delay. The comparators require a reference voltage based on which they determine whether the obtained signal is below or above the desired threshold. For this purpose, we integrated a 12-bit DAC IC to remotely configure the desired switching levels. Lastly, our device integrates an ultra-low noise high PSRR linear regulator used to power the sensitive onboard electronics such as the ADC, and a reference voltage circuit featuring extremely low noise and high stability. In this image, we can see the developed meter. The PCB that features all the presented electronics attaches on top of the BeagleBone board. Next, we proceed by demonstrating the developed API through which the user can configure and instruct the meter. The user is free to insert the resistor values. Similarly, the user can set the amplification level of the employed amplifiers. And of course, the user can set the switching levels among the supported current ranges by properly configuring the DAC IC outputs. In order to acquire a measurement set, the user inserts the desired file name, the sampling rate, the time duration of the experiment, and the channels that she wishes to monitor. Additionally, the user can select whether she wishes to monitor a GPIO channel in order to synchronize the power data with GPIO events occurred on the device under test. When pressing the Start button, the meter initiates a measurement procedure, while the corresponding message field reports the state of the card. After the completion of the measurement cycle, the user can download the measurements by clicking on the Download button. Notably, the downloaded folder contains all the raw files acquired as well as the final calculated data. In order to validate the accuracy of the proposed power meter, we developed two boards able to provide variable power consumption. The first board, illustrated on the left, features several resistors of fixed values, while the second board on the right has two potentiometers that can produce any given power draw. The illustrated figure plots the obtained error. Apparently, the proposed device features a maximum error of 1.6% obtained at 1 mV input voltage of the MAX 9923 current amplifier. It is worth noting that the average error is only 0.45%, which illustrates an outstanding performance. In the first experiment, we monitor the power consumption of the Waspmote device, while it is configured to operate for a few seconds in active state, consuming roughly 22 mA, and for several seconds in sleep state, draining a few hundred microamps. The eProfiler features two LEDs to indicate the active measurement range each time. When both LEDs are off, the device is biased in the nanoampere range. When only the red LED is on, the device measures in the microampere range. While when both LEDs are on, the device measures in the milliampere range. Apparently, the onboard blue LED follows the consumption behavior of the Waspmote device. In this plot, we illustrate the acquired measurements. It is quite interesting that our meter can effectively capture the spike observed when the Waspmote wakes up from the low power sleep. This spike lasts for only a few microseconds. Notably, the competitive power meters are not capable of capturing such fast events when alternating from one bud to another, since they feature notable delays. In order to measure power leveraging all three buds of eProfiler, we employ the EZ430. The EZ430 is configured to operate for a few seconds in active state, draining a few milliamps. After that, for a few seconds in low power mode 0, consuming few nanoamps, and then switches to the low power mode 2, where it drains several hundred microamps. Apparently, this experiment utilizes all three buds of the eProfiler. A close look to the video illustrates that the bud LEDs follow the consumption behavior of the EZ430. The acquired data validate the correct operation of the eProfiler in the different ranges. In the next experiment, we use again the Waspmote device. This time the Waspmote device is instructed to propagate a LoRa packet every 5 seconds. Prior each packet transmission, we artificially asserting high a GPIO pin that is traced with the aid of eProfiler. The illustrated figure plots the power consumption of LoRa interface and the captured GPIO behavior. We observe a delay of 49 milliseconds between a packet transmission instruction and the actual frame transmission. This delay cannot be measured by the device itself, especially in closed source systems that do not provide access to low rosy layers. This is an infeasible process. We repeat the same experiment, but this time we emulate a back-off system that counts down before its LoRa transmission. Again, the delay of the time between the packet transmission instruction and the actual transmission time is obtained through our meter. This functionality of eProfiler is really important when time-critical applications are realized by sensing devices. Similarly, we execute one more experiment employing two different type-keeping circuits, the real-time clock RV1805 and the TPL5111 timer. We configure both circuits to provide periodic interrupt signals, and we use the eProfiler to monitor the accuracy of their timers. Apparently, the RV1805 presents a low accuracy error, introducing a drift of 25 milliseconds after 1 hour of operation, while the TPL 5111 shows 400 milliseconds drift within the same time duration. eProfiler can measure such events for long term, thus can aid the development of time-critical platforms. Lastly, we use the eProfiler to characterize the power consumption profile of the RV1805 real-time clock. The obtained results are illustrated in this figure. The RV dissipates only 17 nanoampere in its timekeeping mode. However, an auto-calibrating function lasting for several seconds is realized in periodic basis, as noted by the increased power draw. Notably, in this scenario, we have configured the RV1805 to provide interrupt signals every 10 seconds, resulting in burst currents of roughly 13 microamps. Our setup highlights the prominence of a high sampling tool featuring extreme dynamic range to obtain high-fidelity power consumption measurements even in nanoampere current ranges. Concluding, the presented power meter features extreme dynamic range of 1 million to 1 while supporting 160 kSamples per second sampling speed and 16 bits of resolution. The eProfiler can be used for long-term monitoring, while it is the first meter that measures ultra-low currents as low as a few nanoamps. Thanks for your attention. Please feel free to ask any question.